Morning, Professor.
Good morning, good morning, good morning. So, how's everybody doing? Okay,
Awake.
awake?
Ish.
that's that's probably about all I can say for myself right now. It's I'm just egregious. Like I don't know why I never grew up.
That's not
You know,
necessarily a bad thing.
yeah, true, but like um, I have a great deal of trouble like getting to work. I have like this ADD problem.
Mm,
I have like this, and um, so uh, um, I spend a lot of time, but I'm always like on tangents, you know.
yeah,
and, then I
no,
get,
I get you.
and I'm like I'll suck down this rabbit hole or that one, and then with all the politics on right now, it's extremely.
Oh,
I
it's,
mean,
yeah,
it's a really interesting time, but it's very challenging.
yeah.
Oh
It's a,
goodness gracious!
it's a
Yeah,
journey.
exactly. Hopefully somewhere good.
Yeah.
Alrighty. So I have a bunch of notes here, and I was thinking to just continue on. Does anybody have any questions, like of what we've been doing or anything like that? Anything burning for anybody? Okie dokie. So so let's talk a little bit about serial dilution. It's just a real quick topic, but uh, if you want to make a calibration curve, a series of reduced series of declining concentrations, uh, you could start with a standard stock solution here. This could be 1,000 part per million cesium in water, for example. You know, and you want to make 1, 3, 4, and 20 parts per million. Right? Micrograms per milliliter is a part per million. Why? Because a milliliter is 1 gram, and 1 microgram is 1 millionth of a gram. So part per million, this is 20 parts per million, right? So, uh, so how could we do this, right? And there's a suggestion off to the side there, I think. But let's just go ahead and I'll use my notes or whatever. So let's see here. So we can say we have a we have 1,000 parts per million. We want 20 parts per million, right? That's our first step. And uh, so probably since we're going to be using C1 V1 equals C2 V2, C2 here is going to equal 20 parts per million, right? And C1 will equal 1,000 parts per million. Right? And then V1 and V2 they're both our choice. And this is where a lot of folks kind of get hung up because it's like too many choices, right? It's not like a single equation that you can just like solve, like a da 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 solve for x, right? So the V1 and V2 choices are like uh, there's these are volume. Actually, V1 is normally a pipette, right? And V2 is normally a volumetric flask. So so that constrains the choices that we have, right? So now, if we use a micropipette, like an adjustable type, then our constraints are basically, like 1 microliter to 1 milliliter, right? It's much less constrained, right? But the final volume, if we're gonna do this in a volumetric way, in sort of a more traditional way, then these are more constrained. Because we have, like, at the very lowest end, we've got 1 ml. 1, 2, 5, 10, 20, 25, 50, 100 mLs, right? And then 250, 500, 1000, right? And so when we think about doing this, there's a few considerations, right? Consideration one is that depending on how precise we want to be, we don't want to use too small of a volume. So we want to ask, are we using too small of a volume? Right? And so, like, if we wanted to do like a 10-fold dilution, right? This is an extreme example, right? E.g., 10x dilution, right? You could take 1 microliter and try to dilute it to 10 microliters, right? But that would be a terrible choice. Because there's a lot of uncertainty in such a small volume, right? So that's a terrible choice there, right? So so let's think about how to do this then. That sort of limits us to, say, maybe, I don't know, maybe these choices. Because a lot of times this is just too much stuff, and it's wasteful, right? It's not very green. And these are actually a little bit hard to handle, and they're a little bit imprecise. Here might be imprecise. So so let's I'll go ahead and start a new page here, and to get onto it here, if we want to make if we have 1,000 parts per million and we want to go to 20, right? Then we're going to use okay. Sorry, and let's do another step here. Then we want to go from 20 to 4, from 4 to 3, and from 4 to 1, right? So these are actually strictly serial dilutions. These are because you take this, you make this, you take this, you make this, etc. So they go one to the next, right? But then the next one is just like too awkward, so you go from here to here. So this is not strictly serial, but I mean it's not serial with the 4, you know. So anyway, I should probably have these arrows pointing out here, but whatever, you get the idea. So we're going to use C1 V1 equals C2 V2, right? And generally the way to do this is just to try it, just to like try some values, right? But let's say the first thing we're going to look at is so we got 1,000 times V1 is going to equal 20 times V2, right? So V1 over V2 is going to equal 20 over 1,000, which also happens to equal, like milliliters, right? 2 over 100. Right? No. I think I have a mistake in my notes. So then we'll go from 1,000 to 20. That's a 100-fold dilution. So yeah, this would be 2 mils to 100 mils, and we can accomplish this. 2 mLs via 1 ml plus 1 ml. Right? This is a pipette. You know, and I think there are 2 mil ball pipettes. You know, ball pipettes available in 1 ml, 2 ml values, right? Okay, so let's see. So what we're going to do is we're going to pipette 2 mLs of 1,000 parts per million stock into 100 ml flask and dilute to the mark with water and mix. And that's just our first step, right? So this is step 1. And then for step 2, we're going to take, and now we need to go from 20 to 4, right? So this is a 5x dilution, right? Because 4 times 5 is 20, right? So C2 here will equal 4. I'm sorry, generalize this for C2 will equal C1 times V1 over V2, right? So C2 is equal to 4 ppm. And what we can do is we can say, well, 5x dilution here, this is going to be 20 parts per million. 5x dilution is going to be 20 mLs over 100 mLs, for example. Or 2 mLs over 10 mLs. Either one of these will work, right? And the precision will be pretty comparable, maybe a little bit better in this case. You know, it depends on your needs, really, as an analyst. If you need absolute precision, then this is best. If you want to do a good job but reduce waste, then maybe that is best. Okay, I'll be right back, guys. Sorry, guys. I had to take a quick bathroom break. Emergency. So let's see here. So that's the second step. We can take a 4 down to a 20 with a 5-fold dilution, right? And that can be 20 over 100 or 2 over 10, right? And then, so let's see then, what would the next one be? We want to go from, we want to make a 3 ppm solution now, right? 3 ppm, right? What we have is 1,000, 20, and 4 ppm. And 1,000, we have 250 mLs, maybe, whatever is left over from that, maybe 230, right? Because we used 20 mils, right? And then we have the 20 ppm, and that let's see here. To make the 20 ppm, we use 100 mLs, 1,000, right? Let's see here. So we have maybe we have 100 mLs of this, and then we used maybe 20 mLs, so we have maybe 80 mLs left, right? So we have about 80 mLs of the 4 part per million solution left. And so, it's either 80 or like 98, right? Because if we went with the small volumes, we have 98. Right? Then we want to go from 4 to 3, right? And 4 to 3 is a little bit awkward, but I happen to know that to go from 4 to 3 parts per million, we can use a 15 ml and a 20 ml pipette, right? This is 3 times 5. This is 4 times 5, right? So this is these cancel. This is a 3 to 4 ratio, right? So C2 here equals C1, and V1 over V2, and C1 is equal to 4, and V1 can be 15, because we have 80, and V2 can be 20, and C2 then will be equal to 3. So this is our next step to make the 3, right? And the next, so this is with pipette, 15 mLs of, let's see, what is this here? 20 ppm, no, 4 ppm, and dilute to 20 mLs to make 3 ppm. And so now we're going to have 20 mLs of 3 ppm. Now the next step is to make 1 ppm. And this is a 1 to 3, right, which is pretty awkward. And so what we can do is we can start with the 4, right, because we still have 80 minus 15 is 65 mLs or so. So that's probably good. So we can take we can get a 25 ml pipette and a 100 ml volumetric flask. Right? This will get us the one factor of 4 dilution, right? So this is B1, this is B2, times C1, which is, let's see, it's 4 parts per million, and this will equal 1 part per million. And so this will take 25 mils of the 4 parts per million dilute to 100 ml to get 1 part per million. Right? So the overall experimental procedure is going to look like we have 250 at 1,000. And we're going to take 20 mLs of this, right? Look like that normally. We're going to dilute that. Oops, I'm sorry. We're going to take 2 mLs of that, and we're going to dilute that to 100 mLs. Right? These are both volumetric flasks, right? And then this is going to be 20 parts per million. And then we're going to take of this 20, we're going to take 15 mLs, and dilute that to, I'm sorry, we're going to take 20 mLs, and dilute to 100 mLs, and then this will give us 4 ppm. And then we're also going to take 25 and then 25 mLs of, oops. Oh, I see. And then we're going to take, 15 mLs and dilute this to 20. And this will give us a serial basis of the 3 ppm. So we're going to do this, and this, and this. This will get us from 1,000. Oops. 1,000 parts per million, down to 20, down to 4, down to 3 parts per million. Then to do 4 to 1, you can just take 20 mLs and then 100 mLs. So this guy is going to respond to this will be 1 ppm. I'm sorry, 25 mLs on this last one. So this will be 1 to 4. This will be 3 to 4. This will be like 1 to 50. Etc. So these guys, this is how you would do this. So there's other ways to do it. You can use burettes. You can start with the same stock solution, etc. I don't really have any bias. If you're worried about gross errors, like you're kind of like shaky on your technique, you might want to start with like this one. If you screw up the first dilution, all the subsequent ones will be messed up. So that might not be good, but sometimes you just have to take that chance. But you can then, you want to go down from 250 all the way to 4, you could probably devise a single step there to do that. Anyhow, so this is serial dilution in great detail here. So let me go back to oils and see what's coming up next. So a lot of the remaining chapter is stuff about, it's basically lab stuff. So we've got micropipettes, how to use them. Just you're going to screw up, right? But try not to suck stuff into the body of the micropipette, because that's bad. Right? Follow these rules. Normally you're going to operate in forward mode. Occasionally you don't operate in reverse. But then, basically set the volume, and there's 2 stops on the plunger. You push it down until feel resistance, and you stick it in the solution, suck up the liquid, touch the side, and then transfer to the receiving volume, and then shoot it all out by going all the way down, right? All the way. So that's how you normally do it. Or you can just go all the way down, take it up, and then shoot it down a little ways. This can be a little bit wasteful. If you only need a small percentage of the pipette volume, then you're going to take an entire plunger full, which is like twice the nominal volume in the pipette. So play with this a little bit. Just read the instructions here. The precision, these are these precisions here go from at worst about 10%, right? Precision and accuracy, really, it's both an issue, right? And I'll talk about that briefly. So, what's the difference between accuracy and precision here, and how do they carry forward? Well, for a small pipette here, 0.2 to 2 microliters, these are really small. This is just, these are tiny little tip. We're just pulling up a tiny little volume, 2 microliters, right? You can expect this guy to give you about 8% error in the accuracy. And this would also be tricky to calibrate, right? Because let's say 10% of the pipette volume is going to be 0.2 microliters. That's going to be 0.2 milligrams, right? And most balances only weigh to the 10th milligram. So you almost can't calibrate this unless you have a microbalance. So, so there's an issue with these really small pipettes. Sometimes you have to use them, right? Just be aware that their accuracy and their precision are kind of, right? So let's talk about accuracy and precision. If these improve as the volumes get larger, right? They improve by getting smaller values, right? 0.5, 0.3, 0.2, right? And these are, I do not know where you're ever going to find 1,000 milliliter pipette. I've seen hundreds, but never found big. Crazy. But these have much better precision and accuracy. These are less than 1%. Right? So these accuracy and precision values improve. Right? So accuracy, if you have a sensitive balance, you can compensate for this. Right? You just weigh water first. You record the temperature, the nominal volume of water, right, say 10 ml, the actual mass of water, use the density to get the actual volume of water. And you can correct for this value. Right? But then you can never correct for this part here. This is really, these parts are like a feature of the pipette. Like it could be a misalignment of the lines, or I don't know, something is weird about the pipette, right? But you can compensate for it, right? But this part here, you can't really compensate. This is estimating your skill at getting just the right amount out. And that's going to depend on the ability to meet the line, and also the surface qualities, how much liquid the surface of the pipette is, and whatnot. So don't expect to exceed this, right? So, so yeah. So this is how these guys work. And accuracy can become to precision. That comes in. I love syringes just because they're super cool, but they're, and you can, a lot of times you can use a GC technique, and you can suck up a little bit of air, suck up a little liquid, and suck up more air, right? Then what you'll have is you'll see the plunger, you'll see some air, then you'll see the liquid, then you'll see some more air, right? You can actually move the little plug up and down, and then you can read the bottom of the plug of liquid and the top, the volumes of it, make the difference and get the volume. It's, you got to be careful because you can't do strong acids because they're steel, and strong acids will dissolve steel, right? Like stainless steel and stuff. But and you got to clean them, right? But otherwise, they're kind of fun to use. Good for small levels, right? And there's other toys, blah blah. Filtration. I will. I think you guys are going to do this in lab, so I'll leave that to Dr. Freeman or Dr. Tompkins. And then calibration of volumetric glassware. Here's a point where we should probably focus a little bit. Let's see. Okay, this is just the normal accuracy and precision that we expect from a piece of glassware, right? And so here, this class A transfer pipeline, so that's a normal resistive class A. Right? And they're certified to deliver 10 plus 1.02, right? And if you calibrate it, you might find that the average volume that transfers is 10.06. Right? And then if you're good, technique-wise, you might get 0.004 in mL, right? This is awfully damn good, but oh well, you know. 4 milligrams and 10 mils. This is really high precision, right? But you want to calibrate it, right? There's a couple of considerations to take into account. First of all, is the thermal expansion of the solution, right? So for thermal expansion, you can use this formula, and it's just that the concentration over density is a constant. So now the density and the concentration of the object of the solution density is the density of the solution, right? So how do I know the density of my goddamn solution, right? Well, in order to do this, we make an approximation that the density of the solution is equal to the density of the water, right? So this is not perfect, but it gets us closer to the truth, right? And so now we have, we can justify ignoring the pipette, right? Borosilicate glass is the pipette or the volumetric glass, right? And they don't expand much near room temperature, right? 0.001% per degree. So that's that can normally be neglected, right? The solution, however, does expand a little bit with temperature, so its density will increase with temperature, right? So as density decreases, so will concentration. Right? So we've got to sort of make a little, we've got to make an adjustment here, right? Because you know, I actually get a little bit confused here. So let's just sort of follow along. We talk about like mass and volume and all this stuff. Now, mass we can measure real reliably with a balance. Right? Volume is a little trickier because the volume of the solution is different at different times. Right? So let's just see how this works. So start with a table like this, right? And you can see here that these numbers all start with 3 nines, or you know, 2 nines and an 8, right? Up to 20 degrees, and then it you get to maybe start getting up to 30 degrees, 0.995, right? Well, it's rarely going to be 30 degrees in the lab, but it's possible. You know, you might have a warm. So what that means is that you'll have a slightly larger volume, you know, and so you'll have 1.05 milliliters per gram. Right? This is gram per ml. This is just 1 over this value in mLs per gram. You know? So you can use a table like this to make a correction using this formula right here. See everything. So, so if you have, if you prepare a certain concentration at a lower temperature, right? Now this is actually the truth at 17 degrees C, right? This is presuming that this is, you know that there are 0.3146 moles per liter when that solution is 17 degrees C, right? But then when you warm it up to 25, the solution expands slightly, so this value is going to go up or down. Well, that value goes down a little bit when you get up to 25. So the way that you do that is you just put in the 17 degree, let's just say 17 and 25. Right? This is 17 degrees, this is 25 degrees. So then you just solve for C prime, you just multiply this by 7. And instead of 3146, you want 3141. So it changed enough fourth digit. Right? So just a word of the wise, this is not going to be used in Chem 55 lab. But as a good chemist, you kind of need to know. Okay? So we're going to just do like a couple of exercises on this, but then we're going to just assume that the densities are essentially 1 on it. We may even do some gravimetric dilution and still ignore this factor, right? Because it's rarely the major source of error. So if we want to, for example, make so if we prepared a buffer solution at 20 degrees C that we cooled it in the fridge, 4 degrees C, then what's the new concentration? Well, first of all, is it going to be higher or lower? Well, 4 degrees C happens actually to be the maximum density of water. So basically this, what's going to happen is you have 1.000 millimolar. You've got this, this sort of volume of solution here. And then this is at 25 degrees C or whatever, at 22 degrees C, right? And then you cool it down, and and basically it shrinks, and it gets a little bit smaller, right? So at 4 degrees C, the concentration is higher. Right? So the way to do that is to use the density of water at 22 degrees C, the density of water at 4 degrees C, and let's see. And this is 0.999974. This is the maximum density. At 1 bar, right? And this is 0.997. And then 773. So basically, this digit here, this changing from the 7 to the 9, that'll make 3 parts per thousand difference in the concentration. So C prime, this is at 4 degrees C. So equals C 22 times density at 22, which is 0.97. Oops. I don't know. This is the right answer. 0.999974 over 0.99773. Oops, I almost didn't see the point at 4 degrees. 1.00. So 0.2%. So that's how to do that calculation. It's just remember that C over rho equals C over rho. And then, so if this is 4 degrees, then we just take the rho value for 4 degrees, and we multiply it through here. This is so this is 1 times 1.00. I guess that's millimolar. Okay. So, all right, that's molar, right? All right. So, let's move forward here. Finish out chapter 2. Yeah. Okay. So, calibration of a pipette. Now, to do this one here, what we have here is a case where you're calibrating a 25 mil pipette, right? And you're going from 10 grams to 35 grams. And basically, you take just a weighing bottle, whatever random mass, right? And you zero the balance, and you weigh 25 ml pipette, 25 ml pipette, and the balance changes from 10.3 to 35.2. Say, well, what was the volume that corresponds to, right? So, know the volume, you're going to need to know the temperature. If you want to do this exactly. So, the mass first is going to be the difference in those two values, 24.912. Okay? And then you're going to take that mass, multiply by the inverse of the density, right? That'll give you the volume at 27 degrees C. Right? And then you can take this mass and multiply it by, there's a third column in that table, which is you can take the mass at whatever temperature and correct it to 20 degrees C, right? So let me go back there real quickly. Right? So you can take this mass, whatever mass you got, multiply it by this value here, and that will tell you the value at 20 degrees C. Right? So so that will give you, that will give you the mass of 20 degrees C. So this is to 27. You use this factor here. It's almost the same factor here. So let's see. Let's test ourselves here. We've got an empty 10 ml ball flask and throw it to the mark at 18 degrees to get 24. Find the volume at 18 and 20 degrees C. So let's say here we've got 14.622 grams, and then 24.581 grams. Right? Take the difference here, and we get 9.959 grams. Right? Actually, it's reverse of that, but whatever. And then the volume at 80 degrees C will equal 9.959 grams times 1.0025 mLs per gram, and that will equal 9.983 grams. Right? Now the volume at 20 degrees, we can use the same mass, 9.959 grams, and we're simply going to multiply by the correction factor to get us to 20 degrees C here. Volume at 20. That guy here is going to be get us to 20 degrees C. That factor there is going to be 1.0029. 1.0029 mLs. And that will equal 9.9. 9.987. Minutes, 8, so it's maybe 988 mLs. This is volume at 18 degrees here. This is mLs. So, shoot, that's all I have time for today. But sort of pacing the class forward here. This is it from lecture 2, right? And this is a good place to stop. So we'll start lecture 3 with instrumental error next time. And please, if you're having trouble with the sampling homework, let me know. There are due dates assigned on sampling now, and they're coming up. So go ahead and work on the sampling homework. Let's see.
Professor,
Yeah.
I didn't see a date for the exams.
Yeah. So the exam, there is something on the syllabus here, and let's see. Files, and then where is my syllabus? That is so weird. Did I lose it somehow? Okay, I promise to get back to you with that information. Okay. It's on the green sheet, wherever that landed.
I don't know if you click week 0 syllabus. I don't know if it's under that, maybe.
Yeah, that's probably it. That's exactly right. So there is a schedule here. So it's week 7, right? So we're way fucking behind this, but whatever. I don't know. You know, we're just gonna have to adjust, right?
Okay.
So we're in like week, we're not that far behind. We're like week 4 now, right? Week 3 anyways. But so we'll do a little bit of we're gonna spend more time on statistics probably than a week. So, but probably Thursday of week 7. Right?
Thursday of week 7.
Yeah, and it is. I am so sorry, but it's not going to be taken.
Okay.
I'm working on one of these brutal respondus thing quizzes because I mean we have to take our pick, right?
Yeah.
Either everybody's going to cheat, or only the very best cheaters are going to cheat, right? And 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 it's not going to be that advantageous to them on respondus, because they're going to be like, how do I got to buy this stuff, and their little eyes are going to be darting around it. I might not get it, but at least you'll be mostly, insulated from that.
Okay. And is the exam probably going to be the same length as class time or 2
Yeah,
hours? Okay,
exactly.
same.
It'll be 50-minute exam, exactly.
Okay.
And yes, and it'll be just like the homework.
Okay.
All righty.
Cool.
How many
Thank
questions
you.
for it?
Yeah. Any other questions?
How many questions are going to be on the exam?
75,000.
Okay.
Yeah. No, I don't know exactly. I don't know. I have to sort of calibrate it a little bit, but I promise it'll be reasonable for the 50 minutes, right?
Okay.
What can I say? It will be less than 75,000. I guarantee you that. Okie dokie. Alrighty, guys.
Thank you.
Have a good
Dr.
day.
Cheryl, thank you.
Bye-bye. Thank you guys very much. I'll talk to you soon.